Okay. Sorry. So my mistake. So I forgot to unmute myself. I got some questions in the chat about the midterm exam, and basically my answer is I don't know. So the questions to the midterm exam, I think it is best if you either ask the TAs directly or perhaps Martin, who is the host of the meeting. Okay, so please questions about the midterm exam to them. I'm not managing much of the midterm exam, so I don't know about the modalities of the midterm exam. Okay, so uh, this is one thing, and now let me come back to what I was talking last time. So last time we were talking about sorting, and I don't want to repeat one more time the initial discussion. And we had the three algorithms which were about the bubble sort, the select sort, and the insert sort. Okay, and these were iterative algorithms, and all they have at least worse time complexity and square. So there are two nested loops, and okay. So it is very easy to see what this does, but the complexity is quadratic. Okay, so and then I will start the review from the next one, which was the merge sort. And now this uses a quite different concept. Okay? This is divide and conquer, where you uh, use a recursive call. Okay, and I remind you, I don't know, so until we manage to remove all the problems with the sites, will always be the natural number. Okay, so the idea of the merge sort was that I want to use the capacity of the merge sort recursively, and I do this by splitting the array into two halves. Okay, and then I use on the two halves, and then I need some recombination procedure. Okay, uh, so I have at this point here, after executing this, I have a sorted array Y, which contains the sorted list of the first half of the elements of X, and then a sorted array Z, which contains a sorted list of the second half of the element in X. But the problem is that not every element in Y is less than or equal to every element in Z. So you need some recombination procedure. And this is the reason why there is always this copying. So the way that this was implemented here was that you copy first the the so you have an array X, and then you copy this into two parts Y and Z. Okay, and then you sort them. You sort this call. Okay, and then you merge. Okay, so so this is what this merging procedure, this merging calls. So if you have two sorted arrays, it combines them correctly to give you a sorted array X. Okay. And then we discussed this animation in some detail. So I do not want to repeat all this, but important is that we use the recursive call of this array. So we split the array into halves and then into quarters, and then we sort these pieces, and then you need this merging procedure, which goes like it compares always the first element of the one side with the first element the other side, and then it takes the smaller one over. Okay, so I remind you in the way that the code was written here. So the way that the code was written here, it does it from the other side. So this one will merge from the right, while the animation merges from the left. But okay, both methods are equivalent, so they have the same complexity in etc. So this was the idea, and now okay, we were able to prove it's not very difficult to see that both the copying and the merging are linear. So this will give you O of n, and you have two recursive calls on an array of the size n half. So by master theorem, for example, you can prove that the complexity is O n log of n. Okay, and then we were talking about the memory consumption, and I made some remark there. So the way that it is made in this animation, okay, is that you have to copy, okay, you have to copy every element at least as many times as is the depth of the recursion. And since the size of the array decreases by a factor by half, the depth is log of n, so every element must be copied log of n times. This means you have a memory consumption of n times log of n, if you count this way. But then I discussed this issue that you can, if you do not use this parallelly, you can reduce the memory consumption by using the same memory for different times for different merging procedures. Okay, so to let's see. So to make this one more time clear, so we had something like this. So what you could do is, whenever you have your array X, you split it into two halves. Okay, and now you try to sort every memory that you need for sorting Z is not needed when you sort Y. And similarly, every memory that you needed for sorting Y is no longer needed when you sort Z. So you will have some you can have some pieces here allocated, etc., etc., but here there will be nothing at the time. And when Y is done, then you keep Y because you still need to reshuffle it with Z, but you can delete all this, okay? And then you need a memory here, okay? But this is no longer needed. So if you are allowed to use the same memory twice, okay, then you can reduce the memory consumption. And we saw that, in fact, if you do it this way, then you can, okay, then you can get this to O of n. Okay, so this was the one way to do this. The other way to do this, and now there was also a question in the chat from, I think, 2 times before. So to emphasize, you can of course also do the following. You can try to sort the array X without copying. Okay, so instead of copying X to Y and X to Y and X to Z and sorting Y and Z, you can try to sort on X itself. Okay, so so this is now X, and after calling, let's say, X from 1 to n half, and here you will call X from n half to n, or it's n half plus 1 to n. You can do this. So you can try to sort on the array X itself without copying. Then you will have something sorted here, and you will have something sorted here. But the problem is that you want to get it again to something which is completely sorted. Okay, and at that time, there is no way, at least I do not know any way to efficiently perform this merging without creating an extra piece of memory. Okay, this is the problem. So even if you sort the pieces of X onto themselves, for this merging procedure, you will need this extra memory. But again, this is at least very economic in memory, and you can very easily see that at every time only one piece of extra memory is needed. This means, again, you can very easily see that in this way also the memory consumption is O of n. So you can make this efficient and memory efficient comparatively, but you always have this problem. Okay, you always have this problem that you need to copy. Okay, this is a fundamental issue in this merge sort algorithm, that you always need to create an extra copy. And the reason is, okay, again, that at this point here, we do not know whether everything in Y is less than or equal to everything in Z. If you knew that everything in Y is less than or equal to everything in Z, then all this merging procedure would not be necessary. Then I can simply append Z to Y. Okay, but we do not know this, and then we always need to copy. So this is the problem with the merge. Okay. So this was the problem with the merge sort. And then we said there is a way kind of to solve this issue with copying by doing something else. And again, let's see. And so what was the idea? The idea was now uh, to create a splitting of the array X such that everything on the left is less than equal to everything on the right. And when you can do that, then you can simply sort the pieces by themselves, okay? And in the end, you will have a sorted array, and then you can save yourself the copy, okay? So so we want now to achieve that you have something like this. We choose a reference element S, okay, which I will review in a moment. And then here everything is less than S, and let's say here everything is bigger or equal to S. So everything, and then you have this division, okay, by this element S. And this number A, which at the end is equal to B, so A and B are equal at the end. This gives you the position of this element S. Okay. So, and I said for security purposes, we should not sort the element S itself. So you sort this piece and then you sort this piece. And how so the procedure which when you're given an element S does this is given here. Okay, this is this loop. This loop here accomplishes this reshuffling, or let's say this is we'll call this later partition. So maybe for later reference, you will see this that we need this very importantly. So let me call this partition. So this code here accomplishes this partitioning part. I should emphasize that there is no guarantee that S remains at the same place. Okay, so during this process, S itself is moved somewhere in the array. Okay, so the position of S doesn't remain the same. Now, the question is, what is S? And we were discussing this issue several times. So S can be any element in the array. Okay, it can be XL, it can be XR, it can be the middle element. Basically, I don't want to say it doesn't matter. Okay, it matters, but in a priori you have no way of knowing what is a good choice of S. So you can take any element in the array. Okay, so whether this is the middle element, the left element, right element, it doesn't really matter. And then we said also that you can make this random. Okay, you can choose you can choose a random element in the array. Okay, and you have then a random, and I call this element a pivot. Okay. So you can do this partitioning whenever you have a choice of this element S. Okay. And the good thing about this, okay, so let me write it here. So this partitioning was complexity of n. Okay, so this is not too costly. But the problem with this partitioning is that S can land very much on the left or very much on the right. So basically, whatever S you choose, you have no way of knowing how well how much in the middle S will land. So it will land somewhere. It can land very much here or very much there. And this is also the reason why I said you must be careful not to sort the element S itself, because you must ascertain that both recursive calls operate on an array whose size from left to R is smaller. Okay, because otherwise you call the quicksort with itself, and then okay, you will run into an infinite loop. Or simply the execution stack will overflow, and okay, and then your program will shut down. So you must be careful that this recursion terminates at some point. So you must make the array small, and that happens when S. Okay, so this problem occurs when S is the first or the last element, which is a particularly bad case. Okay, so and now why is this bad? Okay, and we did this. We tried to make. Let me try to make a complexity estimate of the quicksort, and complexity depends on the choice of this, on the size of the arrays which are put into this recursive call. Okay, so all of n, so all of n is this piece, so it's the partition. This is all of n, and you have two recursive calls. And now, what is the worst case that can happen is that when this element s with whose location is given by the number a equal to p at the end, is the first or the last, and then you have two recursive calls over arrays of size n minus 1 and 1, and it's very easy to see that this is quadratic. So by by master theorem or whatever. So so this means if s is leftmost element in every recursive call, then you have a quadratic, which is the worst case. So this means okay. So now what happens if you take s to be the second or second last element, then you have instead of n minus 1 and 1, you have n minus 2 and 2. But the problem is the same. So as long as you have a constant here which doesn't depend on n, you always get quadratic, and this leads to this conclusion which we had last time, that in the worst case the quicksort is as bad as the bubble sort. Okay. So which is not very good. So if you just use this, then this is not a very huge improvement over the bubble. And to fix this problem, we were discussing, let's say, an attempt at an improved version of the quicksort, in which we said, okay, let us try to find a pivot element. So this why is it called white here? I don't know. So anyway, so we want to find a pivot element so that this piece and this piece are at least both epsilon times n for some epsilon which is between 0 and 1. So epsilon is between 0 and 1. Okay, and if epsilon is fixed. Okay, now assume that we can choose the pivot element so that we can choose this y so that I don't understand why this is y. Let me, for consistency purposes, let me write s here. Okay, so I want to choose my pivot element so that at the end it lands at least an epsilon of the elements from the left and from the right. Okay, assume that this is possible. Assume that we can do this. Then we can improve our estimate. So what stands now in this box is what I drew here with my not so beautiful mouse writing. So then I get the following. Then instead of n minus 2 comma 2, I have n times epsilon, n times 1 minus epsilon. You must be careful why, when you're further to the middle, this doesn't become worse, but it is very easy to see. So the complexity estimate will come from putting s to be exactly epsilon times n from the left or from the right. Then you have two recursive calls over the size of n times epsilon, n times 1 minus epsilon. and then you get this recursion for the complexity estimate of the quicksand. And now we cannot solve this directly by master theorem because because um, because you have two values on the right of the function which are different arguments. But we saw that we can nevertheless get a solution. So I claim that if Tn satisfies this, then this is Tn is O of n log n when epsilon is fixed. And the proof of this is simply to choose Tn to be of this form, which is the meaning of this German word Ansatz. So I assume that T is of this form, and then I try to prove that T satisfies this equation. Okay. So and the way that this works is I simply put in this form for T of n times epsilon, T of n times 1 minus epsilon on the right. And I said here we have been a little bit sloppy. So we have replaced O of n by n. And then I said, basically, this is because if everything gets multiplied by a constant, then this also, C also gets multiplied by a constant. But to be a little bit more precise, let me write this also for later reference. Let me write this down this way. So instead of n, let me write here lambda times n, okay? Where lambda is some positive constant. And then you have an equation of this sort. And now, basically, what you need is now you need that this piece, okay? You need that this piece is less than equal to 0. This is what you need. So choose C so that this is less than equal to 0. And now we said that we consider this piece, which I called star in parentheses, and we observed a few things about this star. So this coefficient in front of the C is negative, okay, and this means that when I can choose C to be minus lambda over this, okay, then C times the star plus lambda is equal to 0. So I can do like that. So remember this formula, and now this is a positive number. So this means whenever I have an epsilon which does not depend on the capital N, such that I can choose my pivot at least epsilon from the left and from the right, I can find a constant C which depends on this epsilon. So that T of n is C times n log of n, and then this will give me the estimate O of n log of n. Okay. I made this remark. What happens when epsilon goes to 0? So then I said that this expression, so the purple expression also goes to 0. Okay, and then C goes to infinity. I emphasize that this is, so star is negative, so this minus will cancel with the negative of the star. When star goes to 0, this will go to infinity. So what does this say? I mean, this says if we allow our pivot to be closer and closer to the boundary, then the worse and worse gets this complexity estimate. And we saw that in general, when there is no epsilon, this means for every epsilon positive this is wrong, then this complexity will go over any constant times n times log of n, and this is true because we saw that the complexity is n squared, which is asymptotically more than any constant times n times log of n. Okay, so this is the what happens when your pivot element becomes worse and worse, more badly and badly chosen. Okay. So this is the in the limit you get the worst case. Okay. Okay. So remember this formula. Okay. So I do not want now to write it down one more time, but for later reference, remember this formula. I will come back to it later because I will do some analysis of constants, which is a little bit unusual, but okay, I'm a mathematician, I can do a little bit more mathematics. So we'll come to this formula later, but the important point was that if I can ascertain that my pivot is chosen for some specific epsilon bigger than 0, then I have O(n) log of n. And I will give you now an algorithm which is linear time. So this is important because I mean I have to keep this O of n here. If the algorithm is too slow, then it doesn't help me much. So I will give you an algorithm which is linear time and works for 0, epsilon is equal to 0.3. Okay, so this will come next. And when you use this algorithm in combination with this quicksort, then you can prove that the quicksort becomes n times log of n, so it really becomes quick. So the quicksort is quick when it is added with this extra algorithm to find a pivot element S which satisfies epsilon is equal to 0.3. So now let me erase this whole mess here. And remember the partition. So we need, and this now it is given in the book as an exercise, but Professor Martin likes this a lot, so I will discuss it in great detail, even in more detail than he himself discusses. So this will probably be the topic for the rest of the class, and it is somewhat involved. So you have to get you have to pay attention. So I mean, we have been now 5 weeks into the semester, so we can start doing a little bit more complicated stuff. So how does this go? So and the first thing is that this is framed here in this stage of the slide. Remember this piece. These pieces will be very important. Again, this will be called partition. So this will be called partition. And what the piece does is, when you're given left and right boundary of some part of the area X and an element Y, which is within this. So, and I don't know why I like always calling this S. So let me call this S. So again, the function of this partition was that. Okay, keep this in mind, because we will need this now. We need this partition piece as an extra procedure. You will see this. You will see in a moment why. So, and we'll talk now about the median revisited, which is the algorithm that you use to output a good pivot element, pivot element S. Okay. So now, what is the idea? And now I again, so for consistency, I should immediately, so that you do not get confused. Okay. What stands here is nothing but the partition function. So I make myself an extra code for the partition. So what did the partition do? I drew it just a couple of seconds ago, but to repeat. So this splits an array XL until R into 2 pieces, L until M and M plus 1 until R, such that everything on the left is less than S and everything on the right is big equal to S, and returns the position of the element S. Okay. Okay, so this is the we will need this code. Okay, this was the code that was in the frame. And then I need to remind you about the order statistics. So let me see. Um, what was the order statistics? Now we had this in section 2. Okay, and we discussed this story. So the order statistics was that if you're given an array and an element k, a number k between 0 and the size of the array, you want the index of the element in the array so that the smaller elements are exactly k. Or let's say I write it in this way here. Since they do not need to be exactly k, they should satisfy this inequality. Okay, but now, I mean, for technical reasons, in order not to stumble over small stones, okay, I want to say it this way. Let us assume that the array elements are all distinct. This is not, I mean, this is not a very strong restriction. So for example, you can simply take a pair consisting of the array element in its index in the array and sort graphically. Okay, so making the elements, the array elements distinct is not a strong technical restrictions, but it is helpful because I do not want to have here inequalities. Basically, once you assume that all the elements are distinct, then this set and this set differ by exactly one element, namely xm, and then instead of continuously writing, instead of writing this way, you can simply write much faster. You can simply write k is equal to the right set. Okay. So this. Once you assume all the elements are distinct, then you do not need to write it in this complicated way. And it is helpful because later, when I use the order statistics, I really want to have a unique element output for every k. Okay, so I do not want to bother with ambiguous k and ambiguous elements and so on. Okay, this is the reason why I made this assumption that all the elements are distinct. So then you can simplify this this statistic specification to that. Okay, and now we were discussing this before. The statistics, and I do not want now to switch to the slides of the last section because it takes me now too much time to get out of the window and in the other one. Okay, but to remind you what we said about case order statistics in section 2, we said there is a quadratic algorithm which is very naive. This will be too slow for us, so we cannot use that. And we said if the array is ordered, then there is an O of 1 algorithm because I can simply output k itself. Okay, but this is not helpful for because our array is not ordered. I mean, we are trying to order the array, so obviously we cannot do like that. And now what you will see at the end of this discussion is that it is possible to have a linear time algorithm for case order statistics, which does not assume that the array is ordered. Okay. So just as an upshot, but we will need this capacity in our construction. Okay, so now remember we have now two pieces, which is partition and the case order statistics. And what is the idea? Okay, so what is my algorithm supposed to output? And this is what is called the median of 5 medians. So now what does this mean? So the idea is that I split my array X into groups of 5. And before I continue, the question came in the chat last semester, and probably some of you immediately ask yourself this question again: why 5? And I will talk about this in great detail, but for the time being, assume that, let us fix that the size is 5. So I'm splitting my array X into small arrays of size 5. Okay. So this means there are n, capital N over 5 such smaller pieces. If n is not divisible by 5, then fill the last piece by something. Okay, so this doesn't really change the complexity too much. And I will try now to output the median of the medians of these groups. So every group of 5 has a median. Okay, so every group of 5 contains 5 elements of the array X. So there is some middle element in, when you order these 5 elements, there is a middle element which is a median. So this is the median of the 5 groups, and this is what is indicated by these black dots. So these are the medians of the 5 groups. And then these black dots themselves, you can consider them as an array, and you can take the median of this median. Again, so I mean, if the number of groups is even, then there are 2 middle elements, and you can pick one of the 2. Okay, so assume that you have this median of median. So these are the medians here. So these are the 5 medians. Okay. And this is the median of the 5 medians. So now it's not very legible, but I'm saying it. And this is what the algorithm is supposed to output. So our algorithm will output you this element. And this is why we call the algorithm the median of 5 medians. Okay. So now, what is good about this element? I claim that this element is a good choice, satisfies this property, okay, which is here in the bottom. Put in the spotlight. So, this element satisfies this. So the element is at least 0.3 times n away from the smallest element. It is at least 0.3 away from the largest element. Okay. This is the property of this element X. And this is what, so to go back to quicksort, this is what we were looking for, right? So if we can output this median, then I can choose this median of the 5 medians as a pivot element. Okay, and this is now, so this is my epsilon. Okay, and here is 1 minus epsilon. Okay, so this means at least epsilon times n from the left, and epsilon times 1 minus epsilon times n from 1 epsilon times n from the right. Okay, so this means the median of 5 medians is a good choice of pivot element for the quicksort algorithm. And the question is now, okay, so first, why do we get this number? Okay, so why, this, I should explain this. So why do we get this, number? And basically you have to look at the picture. So what are elements that you can arguably prove bigger than the median? So you know, in every group, the black dot is less than all the elements which are above. So this means this is less than that, and this is less than that. Okay. So you do not necessarily say that these 2 elements compare in some way. Okay? You only know that this is in the middle. Okay? And similarly, you know that since this is the median, this is less than everything of any of those. Okay. And now, for example, if you have this element, then this is less than that, and this is less than that. So by transitivity, you know that all elements which are above the medians of the groups right of this middle group, okay, they are all less than my element X. Okay, so now I'm using this facility a little bit too much, but now count the elements which are in this red 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 area. So how many elements are there? Obviously, of course, the elements which are above the above x in the same group, they're also there. So now how many elements do you have? You have 3/5, 3 out of 5 elements in each group, and you have half of the group times 1/2. And 3/5 times 1/2 gives you 3/10, and this is what stands here. Okay. And now, or let's say, better to say, no, to be precise, 1 minus this number stands here, okay, because we proved that there are at least 30% larger elements. So now, how do you get this one? You get the left inequality. So the left inequality here, this one, you get by doing something similar. By estimating the size of this piece. Okay, now it's completely analogous. Everything which is below is less than the median, and all the medians which are left of this the median x are less than x. So now again, because this is less than that, and this is less than that, this means that this is less than that. So everything in the red area is less than the element x, and again by the same argument, you see that at least 30% of the elements in this in the whole area n are in this red area. So this means that there are at least 30% of the elements in the area are less than x, and then you have this 0.3. This is where this comes from. Okay, so so we argued now that we can, if we find the median of 5 medians, it will be a good choice of pivot element for epsilon is equal to 0.3. Okay. So now the question is, how do you find it? And important is, this shouldn't be too costly. So we want to have it in linear time. This is important. So I mean, if this is not linear time, then we don't gain much from this whole from this whole algorithm. So now, how do we do this? And I mean, the idea of this is pretty clever, but it is somewhat involved. Okay, and, you have to exercise yourself a little bit to understand. So we need two pieces, which is the order statistics, so the order statistics, and the approximate median. So we need these two pieces. Now, what is the order statistics supposed to do? So we had this before, and now I said we make now a new procedure for the order statistics. So order statistics was, if I'm given an array, and for technical reason, again, I assume that there is a left and right, and k is between 0 and the size of the array, which is r minus l plus 1, then it should output me the index of element in this array, such that the smaller elements than this one are exactly k. Okay, this is what the order statistic was supposed to do. And the approximate median is supposed to return you a median, or let's say an element which approximates the median with precision 0.3, so like the median of 5 median. So approximate median is supposed to mean an element which is not exactly the median, but is at least 0.3 times n away from the left and the right boundary of the array when you start it. Okay. So, and the interesting thing about this construction is that both procedures need each other. I mean, every order statistics needs the approximate median, and the approximate median will need the order statistics. So how do I accomplish order statistics? Okay, so what will the order statistics do? How do I do it? I call first the approximate median to determine an approximate median of x. So what I have now, when I draw this one, let me draw it. I have here my piece from XL to XR. Okay, and the approximate median will return me an element S inside this area, which is not too small and not too large. So then I call this partition, and now this is why I said the split is partition. So now I use this capacity, which was in the beginning of the old implementation of the quicksort. Now what does the partition do? So when the partition is called, what this does is it moves me my S somewhere, and then everything is less than S, and everything is bigger. Okay. So and now the important thing why we need this choice of S is that I can now ascertain the way that approximate median is supposed to work. I can now ascertain that this here is bigger than 0.3 times n, and this is also bigger than 0.3 times n. Okay, and this is important. So as where after you call the partition capacity, this element does not land too far left or too far right. There is at least 0.3 n on the left and on the right. Okay, and now when you have this, then you can. This is what is proceed to the left, proceed to the left or to the right. What does this mean? I mean, if Martin is giving the lecture, he will simply say, think about it. But let me explain. So, what does this do? Okay. So now there are two. To remind you also that this the partition function also returns this value a. Okay. And now there are basically two there are basically cases. A is bigger than k, a is less than k, and a is big, a is equal to k is bigger, less than k is bigger than k. When a is equal to k, then you can simply return s itself. Okay, so this case is very easy. So what happens when a is less than k? Okay, this means that the elements here you're seeking an element which has more smaller elements than the element s. And you know how many smaller elements s has, namely it has a smaller element. What you can do is you can simply let me call this maybe left or right. So you call this on the right piece, and you use k minus a. So you call the order statistics on the right piece by so you set L to a, and you call the order recursively on the right piece by decreasing k by the number of a, because you know that there are a elements which are already smaller, and on this piece you need k minus a smaller element. Okay, so this is what you do here, and when a is bigger than k, then you simply call it on the left. Okay, so then you simply call it on the end with k. So because you know S has already more smaller elements than what you wanted, so this means that the element with k smaller elements must be somewhere on the left. So okay, so now in detail what this is supposed to mean. So now I have so this heuristics here is what this is supposed to mean. So it is. I didn't write the pseudocode directly, but I made it much more detailed than Professor Martin. That's why it shouldn't be too difficult to see what the pseudocode of this is supposed to be. Okay, so this is the order statistics, and now you need the other piece, which is the approximate median. So now this is, I mean, this is what we are supposed to to output. Okay, but we need the order statistics for that. And how does this go? So now this is now easy. So once you have the order statistics, what you do is you you split the array into groups of 5. Okay, so you build these vertical blocks in the previous drawing. So then you find the median in each group. And how do you find the median? It is not very relevant in the sense that as long as you do not consider constants, which we will do later. Okay, so I will go into great detail later, but as long as you ignore constants, asymptotical constants, it doesn't really matter how you find this median. So you have a group of 5 elements, and you can use various algorithms. So obviously, when you sort the array, you can find the median later in the middle of the array. So, for example, you can quick sort it and take the middle element. Okay, but it doesn't really matter. So important is that this can be done. It depends only on the size of the group. Okay, but so you can do this with linear cost. Maybe I should let me write this here. There is no problem of doing this with linear cost. Okay, and then you can use the order statistics capacity to determine the median. Why? Because, well, what does order statistics do? The order statistics gives you an element which has a given number of smaller elements. Okay, now when the groups are 5, there are n over 5 of these groups. Okay, so now you have the array of the black dots. Okay, so you have this array of the black dots. You consider only the black dots. So this has size n over 5. Okay, and now you call order statistics with k is equal to half of this, which is n over 10. Okay, and so in particular, when you set k to be half of the size of the array, so here, so when k is half of l r minus l plus 1 or whatever, okay, this order statistics would in particular will output you the precise median. Okay, so now this means I have an array of capital N over 5 medians of 5 groups. I call order statistics with half of this size, which is capital N over 10, and this will output me. Okay, this will output me this element, which is the median of the 5 medians. Okay, so now I mean, it is a very, this is why Martin likes it. So this is a very clever algorithm. I mean, it has 2 pieces, so the order statistics and the approximate median, and they both need each other. Okay, so the one itself, so order statistics needs also itself. Okay, because you need to call it recursively on smaller pieces, but order statistics needs approximate median, and approximate median needs the order statistics. So they need to call each other recursively, and this is what accomplishes this task. And you must be careful. I mean, just if you look at it, to see that the array size decreases. So order statistics, when it calls it recursively, the array size decreases. When order statistics calls the approximate median, the size does not decrease. But when approximate median calls order statistics, then the size decreases by the factor of 5. So it is not difficult to see. It is not difficult to see that but it's important to notice that the algorithm doesn't run into a loop, so the recursion depth is finite. So after the algorithm will terminate and will give you the correct result. Okay. So it requires a little bit of thinking. Okay, this is not easy. Okay, but I mean this is the value of this idea, is that okay, this is it requires some idea, okay, to make it in this way. So you have two pieces, and each piece needs the other. Okay, now I return to this question because it is I mean it is a justified question. Why 5? Okay, and so let us do the complexity estimate. You cannot do this. You cannot do this straightforwardly, but you need two equations. So let's say I have an array of size small n. Okay, so before this it was capital N, now I write small n, but it doesn't matter too much. So I try to estimate the complexity of this algorithm. Now, so what happens for let's do first the order statistics. So the order statistics, the complexity of the order statistics is the complexity of the approximate median. So this is TO is for order statistics and TH for the approximate median. And then you have O of n, so this comes from the partition. So this comes from the partition. And now comes this term. And again, to make clear what this term means, we said I do not want to make this drawing again. But we saw that after calling the approximate median, you need to call order statistics recursively. And the function of this approximate median is to restrict the maximal possible size of an array onto which you call TO recursively. Since you know that this approximate median is at least 30% of the elements from the left and from the right, the biggest array, possible array onto which you call onto which order stat calls itself recursively has size at most 70% of the size of the original array. Okay, so this is where you need this approximate median. So you need to bound the size of this array that you call order statistics recursively on. So the quality of approximate median enters into this term. So this is how you get the equation for the order statistics complexity. And now we need to make a similar equation for the approximate median. So the approximate median, what do you get as a complexity there? So you need this O of n. Okay, now here I write capital N. Now here it was written small n, but this O of n here is that one. Okay, so this is the effort that you need to determine the median of the 5 groups. Okay. And as I said, as long as you do not care about constants, it doesn't really matter what algorithm you write, but keep this in mind that this O of n, the constant in this O of n, does depend on how many operations you need to find this median in the group. But as long as you do not care about constant, you can simply write O of n. So this O of n, okay, this O of n comes from here. And now you have these two equations. And so what do you see from there? Now I claim, I claim that from these two equations you can see that TA and TO are linear. Yeah. And this is what you wanted. So the goal of this calculation is to see that capital TA and capital TO are linear. And you cannot do this exactly by master theorem. Now you have two equations. You cannot do this too. I mean, you do not. I mean, don't be too concerned if you don't see it immediately. The important point, okay, in this whole story, why this works, okay, why is this number and this number, and 0.2 plus 0.7 is equal to 0.9. Now, what is important about this is that it is strictly less than 1. And this is what you need. So by using this fact that the constants that occur here and here are together are the sum is less than 1, you can prove that TA is a linear function. Okay. So now you probably don't immediately. So now I will make it more clear. So this property for 5 groups that you get something less than 1 is what is important to prove that if you do it with 5 groups, you get something linear. And now let me try to do this whole thing now for one more time for other types of groups, to return to the question, why do we need 5 groups? Do we really need 5 groups, and how important it is to choose 5 groups? So now I have to still have to erase some things here because it's so now I will return to this question. I made an extra material to explain what happens if you take other sides of groups. This is also part of your homework. So I mean, I'm aware of this fact, but um, to okay, so to make clear, or let's say to examine this question, which I mean, this is a meta question. So the question is, why do I need to take 5? Okay, so why do I need to take groups of 5? And this is now a little bit more delicate, and probably I will not be able to do this until the end. Maybe I will probably have to continue next time. But I simply did this whole calculation for other groups. Okay, so what happens if you take a group of k and instead of 5? So now there is a little bit of difference between even and odd k. So let us first do the case that k is odd. So let me try to draw it. Like you see, I mean, my drawing skills are always in this context probably leave to be desired, but So what happens if you take other values of k which are odd? So for example, 7 or 3. Okay. What happens then? Then I can modify this picture. So I have there is the important point about odd is that there is always a middle element. Okay, when you have an odd group, there is always a middle element. So when the group is odd, there is a middle element, and then I have a picture like this with the red curve. And now let me try to poorly kind of recreate this picture like this. Okay, you have so and this will be the element x. Okay, you can make this picture also for any other odd group. Okay, there is nothing wrong with that. And then what will happen is that the elements above, including the middle element, so here you will have k plus 1 over 2k. So this is the number of elements in a group of k, including the middle element. So for example, when you put k is equal to 5, then 5 plus 1 over 10 gives you 3. Over 2, sorry. Plus 1 over 2. 5 plus 1 over 2 gives you 3. Okay. So you have this group of k plus 1 over 2 elements. So now when you I do not want to make this now in every detail. What happens for these formulas that we had at the bottom in the yellow when you change the group size of k is equal to 5 to some odd k? Okay, so the formula for the approximate median remains, and except that you have now groups of size n over k, so you have q of n over k, and this O of n, I said it, but for later reference, this O of n will be the effort that you make to determine the medians of these 5 groups. And now I said basically, as long as you don't care about constants, it doesn't matter what algorithm you use to determine this median. But to be more precise, let us say that we need 5k operations to determine the median in a group of k. So so then you will have n over k groups times phi of k operations, so you will have this complexity of determining this tick-tock. And in the second formula is what happens with the formula for TO, so for the order statistics. It calls an approximate median. Then you have this partition function. So it's written this O n independent of k comes from the partition. So this O of n comes from the partition, and it doesn't depend on k. The partition capacity has nothing to do with k, so this doesn't depend on k. And then you have to modify this 0.7. So what is 0.7? So 0.7 means you have 3 of the groups of 5 and half of the groups and 1 minus that. And now instead of 3 over 5, you have k plus 1 over 2k. Because you have this divided by the size of the group. So k plus 1 over 2k. And since approximately half of the groups on right and half of the groups on left, you have 1/2. And then you have to take 1 minus that. And to check that you calculate correctly, you simply put k is equal to 5, and then you have 1 over 2 times 6 over 10, and this gives you 0.3, and 1 minus 0.3 gives you 0.7. So this is the generalization for other k of this number 0.7. So when k is equal to when k is equal to 5, then this number here is equal to 0.7. So this is what happens when you have odd groups. And now what happens when you have even groups? Yeah, and then you have the reason why even is not good or not so good is that in an even group you have 2 middle elements. Okay? And this makes the efficiency worse. So when you have a group of of even elements, let's say 6, then there are 2 middle elements. Okay, and the question is now which one you choose. Do you choose the upper one or the lower one? And what happens if you choose the upper one? Okay, the problem is whichever you choose, the estimate will get a little bit worse, because if you choose the upper one, then these groups here on the right, so which feature this one and above, will have exactly 1/2, will have exactly k/2, and this will have k/2 plus 1, but you're interested only in the smaller one, so the smallest number of elements that this is away from the boundary. It's whether you choose this one or that one. Okay? You always have on the one side k/2 and the other side k/2 plus 1, but this is a smaller method, you always have k/2. Okay, and then this way, instead of k plus 1 over 2k, you just get k over 2k, so 1/2 times k over 2k gives you a quarter. Okay? So, and this is where this number comes from for even n. So for even n, the median that you output will be at least a quarter away from the boundary. Okay, and this is where this number comes from. The rest remains the same. And now let me finish here, okay, because I am running out of time. So I will continue this discussion the next time. So remember these formulas for the complexity. So what happens if I use the median of k medians? There are these two formulas of the complexity, and I will continue with this next time, and you will see what happens if you use the median of other group sizes. Except 5. You will see that 5 is special in some way, but it is not the best.